Today we are going to see generating function for J and X for Bessel function. Okay, generating function. Here exponential x by 2 z minus 1 by z. This is the generating function for the Bessel function. Okay, that we can prove. Generating function means from this function we can obtain Bessel function. From this we can obtain the Bessel function. That is meant by the generating function. Okay. So what we do is we write exponential x by 2 z minus 1 by z as exponential x z by 2, okay, into exponential minus x by 2z. So we are writing this as exponential x by 2 into exponential minus x by 2z. We know that exponential x, that is given by 1 plus x by 1 factorial, x square by 2 factorial, x cube by 3 factorial, etc. the infinite series. So using that I am writing exponential xz by 2 as 1 plus xz by 2 plus 1 by 2 factorial xz by 2 square 1 by 3 factorial, okay, 1 by n factorial xz by 2 to the power n, that is the nth term, and it continues, it's infinite series. Okay, so it continues. Okay, anyway, actually we need the terms after the nth term. So nth term is this, nth term is this, then the next term will be this 1 by n plus 1 factorial xz by 2 to the power n plus 1, 1 by n plus 2 factorial xz by 2 to the power n plus 2, etc. In the same way we expand this exponential minus xz by 2. So 1 minus x by 2 z, okay, alternating plus n minus n, minus x by 2 z plus 1 by 2 factorial x by 2 z square minus 1 by 3 factorial x by 2 z whole cube, okay, then plus minus this is nth term, minus 1 to the power n, 1 by n factorial x by 2 z to the power n, okay, then the next term is minus 1 to the power n plus 1, 1 by n plus 1 factorial x by 2 z n plus 1, and then minus 1 to the power n plus 2. Okay, so these are the terms. Then what we do is we multiply this equation. This is equation 1. This is equation 1. Okay, this is equation 1, and this is equation 2. Okay, and what we do is we multiply equation 1 with 2. Okay, we'll multiply equation 1 with 2. So as we multiply, we will be, this is a series in terms of set, powers of set. This is a series in terms of again power of set. Okay, the negative, in fact this is z minus 1, z minus 2, z minus 3, etc. So what we going to do is we want the coefficient, okay, coefficient of z raised to n in this product. So when you multiply these two equations, what you want to get is the coefficient of z raised to n. See how we get z raised to n. Actually, the multiplying means multiplying each term of the series with every term of the series, second series. Okay, multiplying each term of the series with every term of the second series. So when I multiply this term with this, then I have set to the power n here. Okay, set to the power n. When I multiply this with this, set to the power n will be there, and the coefficient will be 1 by n factorial x by 2 to the power n. Okay, so the coefficient is 1 by n factorial. As I multiply, I will get 1 by n factorial x by 2 to the power n. Okay, and then when I multiply this term with this, okay, here's in the numerator, here we have set to the power n plus 1, in the denominator set. So as they combine, as you take the product, you will get z raised to n, and the coefficient will be minus 1 by n plus 1 factorial x by 2 to the power n plus 1. Okay, x by 2 to the power n plus 1, and it goes on like that. Okay, x by to the power 2 set. Okay, let me see. Yeah. Okay. Here I have the x by 2 to the power n. Yes, this is n plus 1. Sorry, this is x by 2 to the power n. Here x by 2 to the power n plus 1. Then yes, x by 2 to the power n plus 2. Oh, sorry. Okay, 1 by n plus 1 factorial x by 2 to the power n plus 2, isn't it? I think that's what you said. X by 2 to the power. Okay. Here. Okay. X by 2 set. Okay, this is x by 2 set. Okay, that's why we have x by 2 set here. Okay, see x by 2 set, x by 2 set. Okay. So yes. So this is here I have x by 2 power n plus 1. Here I will get x by 2 to the power 1. So I should be getting x by 2 to the power n plus 2 here. Okay. So I will be getting this. As I multiply and take coefficient of z raised to n in the product, I will be getting this. 1 by n factorial x by 2 to the power n. 1 by n plus 1 factorial x by 2 to the power n plus 2. 1 by 2 factorial this. Okay, and this is exactly Bessel function. This is exactly Bessel function, because we know next Bessel function is this Jnx. Okay, if I am writing here in terms of factorial and plus r factorial, here r factorial. So this is Bessel function. Okay, so as I take the series, I will be getting the first term is 1 by n factorial x by 2 to the power n. The second term is minus, because minus 1 to the power minus n plus 1 factorial x by 2 to the power n plus 2. Okay, so what we have got here, that is exactly the Bessel function. This is Bessel function. Okay, Jn of x. So one can say the coefficient of z raised to n is the Bessel function. The same way you can take the coefficient of z raised to minus n. Okay, how do you get coefficient of z raised to minus n? See, if I multiply this term, coefficient of z raised to minus n. Okay, so not this. If I multiply this with this term, okay, so this will be see, minus 1 to the power n, 1 by n factorial x by 2 to the power n. Okay, here's coefficient of what I am taking is coefficient of z raised to minus n. Okay, so this will I get from multiplying this with this, I will get the first term containing the z raised to minus n. And if I multiply this with this one, I will get the second term containing z raised to minus n. So when we take the coefficient, you will see that it is exactly equal to j minus nx. Okay, coefficient of z raised to minus n is j minus n of x. So if you expand this one, this consists of z, you will be getting a series, infinite series, because it's exponential series, exponential function, so that is an infinite series. It contains powers of z and powers of 1 by z. Okay, the series contains powers of z and powers of 1 by z, and their coefficients, coefficient of z raised to n is what? Jn of x. And coefficient of z raised to minus n is what? J minus n of x. Okay, so you can write this as yes, you can write this as j0, this is the coefficient of z raised to 0, coefficient of z raised to 0, coefficient of z raised to 1 is j1, coefficient of z raised to 2 is j2. Okay, coefficient of z raised to minus 1 is j minus 1, z raised to minus 2, j minus 2, etc. Okay, so generally what we can write is exponential x by 2 z minus 1 by z equal to sigma n equal to minus infinity plus infinity z raised to n Jn of x, z raised to n Jn of x. Okay, so this is what we get. So we say this is the generating function for the Bessel function. Okay, so the generating function is completed. Now let's move on to the next topic, the Bessel integral. Okay. So before that, before going into the Bessel integral, let's see a trigonometric expansion involving Bessel function, which we do from the generating function. We know this is the generating function. We have just seen that this is the generating function. And on the right hand side, I can write J0, Z J1, Z square J2, Z cube J3. Okay. Anything? Yes. This you can write. And here we put Z equal to EI theta. Okay, what I am doing is I am taking this Z as equal to EI theta. So Z is EI theta, 1 by Z is e to the power minus I theta. Okay. So on the left hand side here you will get e to the power x by 2 Z minus 1 by Z as equal to this exponential x by 2 e to the power I theta minus e to the power minus I theta, and on the right hand side we have J0 e to the power I theta J1 etc. J minus e to the power I minus I theta J minus 2, like this. Okay. And now this is exponential I theta by 2i. This is sin theta. We know exponential I theta minus exponential minus I theta by 2i, that is sin theta. Okay, that we know. Exponential I theta plus exponential minus I theta by 2. What is it? Do you know? Exponential. Yes, that is. No. Exponential I theta plus exponential minus I theta by 2. Exponential. Yes, that will be cos theta. And this is sin theta. Okay, by 2i. This will be sin theta. Okay. And also we know j minus n is equal to minus 1 to the power n j n x, that we use here. That means j minus 1 will be minus 1 to the power 1 j1. Similarly, j minus 2, what will be j minus 2? J minus 2 equal to, can you say what will be j minus 2? J minus n is minus 1 to the power n jn. J minus 1 is minus 1 to the power j, so this is equal to minus j1. What about j minus 2? J2. Okay, so that will be j2. Okay, so j minus 3 will be minus j3. J minus 4 will be j4 itself. So even numbers, for even numbers, you know, the negative or the even the j minus 4 or j minus 2, that will be equal to the jn. Okay, that will be equal to jn. J minus n will be jn for even numbers. For odd numbers, j minus n will be equal to minus j. Okay, so here see j minus 1, this is equal to minus j1. Here this is j minus 2, that is equal to j2, and this is j equal to minus j3. So as you can combine this, J1 here, J1 here, you can combine. J2 here, J2 here, you can combine. So you will be getting this exponential I x sine theta, that is equal to J0 plus J1. Okay, I theta minus exponential minus I theta is J2 exponential I2 theta plus exponential minus I2 theta, J3. Okay, I think this is clear to you why we are getting this. Now what I am doing is I divide. I need a 2 here to write it in terms of, here I need 2i to write it in terms of sine theta. Here I need 2 to write in terms of cos theta. Here I need 2i. Yeah. So I can write this exponential, this as 2i sine theta. This is equal to 2i sine theta. This will be 2i sine theta. This will be 2 cos 2 theta. This will be 2 cos 2 theta, and this will be 2i sine 3 theta. Are you getting this? How we are writing it like this? Do you understand what I am doing here? Nobody responding? Okay. Yes, okay, good. So this is see what I have done. I have written here as J1 2i sine theta, here J2 2 cos 2 theta, J3 2i sine 3 theta, and on the left hand side this one I am writing as cos x sine theta plus I sine x sine theta. Okay, cos x sine theta and I sine x sine theta we are writing. So we have this cos x sine theta plus I sine this J0, and what we do is we equate the real and imaginary parts. Real part here is cos x sine theta. So here the real part is J0 to J2 2 cos 2 theta, like that. And when we compare the imaginary part, here we have the imaginary part sin x sin theta. Here I will have J1 sin theta, then J3 sin 3 theta. Okay, so I equate the real and imaginary parts. So what I am getting is cos x sin theta is equal to J0 this, and sin x sin theta is equal to this. Okay, so these equations we are getting for cos x sin theta and sin x sin theta, and these equations are known as Jacobi series. Okay, so what we have done is we have written cos x sin theta and sin x sin theta in terms of Bessel function. Okay, cosine series and sine series can be written in terms of Bessel functions. Okay, and this series is the Jacobi series. Here if we substitute theta equal to pi by 2, okay, sine pi by 2, so you have cos x. It's theta pi by 2, so sine x. Okay, so you will be getting cos x and sine x. Cos x is this J0, this, and sine x is this. J0 minus 2 and sine x is 2J1 minus. Okay, see, so here we have written cos x in terms of Bessel function, and the sine x in terms of the Bessel function. Okay, so let us stop here.